Okay, we're going to practice drawing electric field lines and consider what an electric field map really is. So let's imagine that I've got two positive charges here in the middle, right? And they're stuck on this sheet of paper, right? Two spherical objects. Maybe we'll put a little bit of a shininess on there to make you believe they're spheres, and they're just stuck here. They're positively charged, right? Positively charged, they have a net deficiency of electrons. And imagine that all these black dots on this page are the location of positive test charges. Again, what we're going to do is just imagine that we're going to drop a positive test charge anywhere in this field, and our question is, what is that charge going to do? And this field map is going to help us figure that out. So the first thing we have to realize is that every positive test charge on this sheet is affected by two forces, right? For instance, we can look at this one. Excuse me. This one is affected by the presence of this charge. And by the way, all these charges can move, but these two cannot. This one is affected by this charge, but it's also affected by the presence of this charge at the same time, right? They're both positive. They're both going to be repelling, but it's easy to see that since it's closer to this one, it's going to be a stronger force felt by this charge than the forces felt by this charge. And so what we can do is we can just take a sheet of paper and just imagine a line going straight through the center of those. And I'm going to draw an arrow from this charge along that line. And I want it to be a fairly long arrow this time because this represents the force felt by this charge because of this one. All right, let's draw all the forces from this charge in red. All right, so these are red charges, or red forces, because of the presence of this. So all I want to do with all of these charges is draw the forces felt. Right. So for instance, with this one, it would be exactly the same length, but in a different direction. Again, on a straight line directly away from the force, something like that. Let's go all the way out here, something toward the end. This one's very far away from that one, but it still feels a force, but it's very weak. So I might just put a small little tick of an arrow right there. All right. Take a minute and maybe copy this down on your piece of paper and see if you can draw all the arrows that represent the forces felt because of this one particle. Pause the video. Boom. All right. Yeah, that's pretty crazy, right? All that stuff just showed up. If you drew all the arrows on this picture, it should look something like this. And you might be thinking to yourself, man, that looks like an explosion. Well, yeah, it does, because any of these test charges, again, placed anywhere in this field, will go away from this one. Just imagine that this one's not here for a minute. This will be what will happen if the charge is placed in any of these locations. If we place it close, it experiences very strong force. If we place it very far away, it experiences a force, but it's very weak because of the distance. All right, now I'm going to do the same thing with this charge. I'm going to make believe like this one's not here now and draw vectors on all of these, but this time the vectors are going to be, well, let's make them in green, right? Let's make them in green for this charge. Green vectors representing the force felt on all of these because of the presence of this one charge. Pause the video for a minute and see if you can do that. All right, your pictures to start to look something like this. Here's one vector very close to the green one, experiences a very strong force. Notice that these two are meeting in the middle. We'll talk about why in just a minute. So the same thing with the rest of these. All these green vectors represent the forces felt by these test charges because of the presence of this one. Keep going with your picture. All right, and you should have something that looks like this. I know this is a long, complicated process, but trust me, it has a point. So what you should have on each one of these test charges is two force vectors. And sometimes they're hard to see. For instance, they overlap right here, but there's a red one and there's a green one. There are two forces felt by each of these charges at each of these points because of the presence of these two charges placed in the field. So this one charge, for instance, is going to feel a very strong force in this direction because of the presence of this red charge, but it's also going to feel a force from this green charge in this direction, and it's weak because of the distance between the two. Now, obviously, these charges can't go in two directions at one time, so what we're going to do is draw sort of the resultant vector, right? It's only going to go in one direction. And that one direction is the result of these two forces that are felt. And generally that vector is the direction of that vector is going to be a little bit intermediate between the length of these two and intermediate between the directions of the two. However, the longer the arrow, the more the influence it has on the resultant vector. So this one here, the resultant might be something like this. All right, so I'm going to draw these resultants here now. This resultant will be right in the middle, straight up, because these should be exactly the same. All these middle ones should be exactly the same. This one, the resultant is actually just 0. That's if there's a test charge right exactly in the middle, these two are going to cancel out, and this one should be just slightly longer. Those should be exactly the same length. So we're going to get this one here, this one here. My charges don't look the prettiest in the world, but you get the point. This is all the same direction. The length of the resultant is just intermediate between the two. That one there. Pause the video, see if you can finish that up. All right, so now I've drawn all these vectors. Yours should look something like this. I know that the links are kind of different, and I didn't do the greatest job either. But the point is this. I've highlighted all of our resultant vectors in yellow. And that vector represents what exactly that charge is going to do. Oh, I forgot one. There should be one right here. Right? And I'll highlight that one as well. The point is this. You can trace the directions of all of these field lines, and they will end up making that characteristic field map that we saw earlier. And to do this, let's use pencil. How about that? So I'm going to start from this charge, and I'm going to draw a line that traces where these will go. And you can imagine, you can place these test charges in infinite locations and think about the same thing. What direction would they go? Hopefully you can notice there's a little bit of a pattern here. What's going to happen is the electric field lines are going to go kind of out like this. All right? And they're going to follow the direction of these vectors. As I'm drawing these, I'm just simply tracing what my vectors bore out when I drew. This is simply a consideration of electrostatics. That's all we've done. All right. And we'll draw another one that comes right in here, and we'll do the same thing. The other side is it's very symmetrical. It looks the same. It's a symmetrical diagram. This line looks like this. That one looks like that. On the left and the right, they go straight out from each other because the direction doesn't change on these two. Like this and like this. All right. So now you see, if I back it off a little bit, this is what the electric field map looks like for a positive charge. For two positive charges in a field. We did all of that work, and that's the only time you'll have to do that work. It's a lot of work, but it's a good thing to consider that all of these charges are experiencing two different forces. And because of the presence of those two different forces, we get an electric field that looks like this. Now, you can kind of memorize this for this class because this is what a positive field would look like. You'll see that again. But realize that we can have extremely complicated electrical field maps that can only be drawn with a computer because you can place multiple different charges in here, and that's what you really get in real life is electric fields are three-dimensional. This is only a two-dimensional electric field. But imagine taking this thing and turning it and rotating it around, and what you would see. This is what it would look like with a positive. A couple of more things to consider. Let's just think about this for a minute. Pause the video after I ask the question. How would this change if instead of positive, if these were negative charges? Think about that. How would this electric field map change? Pause the video for a minute. Well, hopefully you came up with the idea that, well, it wouldn't really change very much. The only difference is, if these are all still positive test charges, the directions of the forces are still going to be the same, but, well, actually, the magnitudes are going to be the same, but the directions are different, and the directions are still along the same line, they're just in the opposite direction. So if this is a positive charge, it's not going to be repelled away from this negative, it's going to be drawn towards it. So all these vectors will be drawn in exactly opposite directions, and we could do this entire process all over again, and what you would get, what you would result in is, with a negative field, you would get the lines that look exactly the same except they point in toward the negative. And realize that all of this meets our description of what electric field lines are. You should have your notes that say By convention, the direction of a field is always away from a positive charge and towards a negative charge. So notice, because we use positive test charges, all of our electric field lines went away from the positive charges, but if they're negative, they simply will go in toward the negative charges. So the arrows will be like this, and we would get rid of all the arrows on the outside. So this is what a negative electric field would look like. Point is this: if you have two of the same charges, the field lines will look kind of like spider-like this. They look exactly the same. But if it's negative, they point in toward the charges because the electric field lines go toward negatives and they go away from positives. Let's consider this next one real quick, a positive-negative field. This is going to be faster, but let's consider the same thing. If we consider this one red and this one green, let's just think about this charge right here first. This charge is going to, it's a positive test charge again. Well, what's it going to do because of the presence of this one? Well, positives repel, so this one's going to repel with a decent amount of force. But then what is this charge going to do because of the presence of this red one? Well, positives are attracted to negatives, and it's pretty close. So this force vector has to be actually longer, and it's towards, so that vector is going to look like that. And if we do the same thing we did before and draw the resultant, that resultant would be something like this. Right? See if you can do that if you want to for all of these. Think about what those would look like. I'm going to pause the video and do them all for you, and we'll look at it. There are all the force lines because of the presence of the green positive charge. Notice that those look all the same as the green ones that we drew for the green positive charge on this side. Now I'm going to draw the ones for this red negative charge. All the red force vectors represent the forces felt by all these positive test charges because of the presence of this red negative charge. Okay, all these are positive, so they will be attracted to the negative charge. That's why all the force vectors go this way. And then we'll do the same thing where we draw the resultant vectors as we did here. Here's what those guys look like. All right, all of the resultant vectors are highlighted. I'm going to highlight them now. You can see that these field lines start to look quite a bit different, all right, because of the presence of this negative. And if we trace them all and draw the field lines like we did before, we get something like this. Away from a positive towards a negative. Away from a positive towards a negative. Away from a positive and towards a negative, all right? Almost like these concentric circles that keep happening. That if you place a positive test charge anywhere in this field, this is what it would do. We go away from the positive and toward the negative, and because of the presence of both of these are the paths that they would follow. If it's anywhere in the middle on this line, it would go straight there. Anywhere on the outside would follow this curved path because of the presence of those two charges that cannot move. So you need to also memorize this characteristic rainbow type shape, like a double rainbow type shape almost, that this is the shape of a positive negative, a dipole, in other words, electric field map. So you'll see this one, this is a positive negative, away from the positive and toward the negative, and you'll see this one, a negative negative or a positive positive. Two of the same charges look like spider legs kind of going away from each other, all away from the charges, leaving this sort of empty space in the middle. So there you have it. Those are your electric field maps. Positive positive or negative negative electric field map, and the electric field map for positive negative and electric dipole in the field. Again, these can get very much more complicated. We can get into three-dimensional things that can only be dealt with computers, but we're not going to do that today.